This is again a problems class rather than a lecture, so I'll be going through some old exercises or any questions that you care to send through about the text. I'm getting very few of those, so I'm assuming and then everything is going well. So let's see then. I'll do questions that were like on last week's homework sheet and things around in that neighborhood, unless you ask for anything, anything else. So let's see what is on the list there. Let's look at 434. Exercise 434, you were asked to do 1 and 3. Show that 1, a set of countable subsets of R has cardinality 2 to the LF0. Okay, so just to recall, what are we talking about here? Right. Let me just make sure I've got my lemma numbers correct here, so I don't say the wrong thing. So I don't have these numbers off by heart. So we're just saying that so 414. So this is an aside here, right? What does countable mean? So definition 414. Okay, that means that there's a one-to-one map of X into omega. So it could actually be finite. Right? We say countably infinite to mean just that it's one-to-one map of it into omega, but it's also infinite. So officially speaking, finites are countable down in here. Right? So 2 to the LF0, the other term in the question. This is the same as, it's also called 2 to the omega 0, or what we would just call 2 to the omega here. So this is the cardinality of the set of functions which go from here into here. And we know that the cardinality of the real line is the same as that of this set of functions. Right, so there's a bijection between R and the power set of omega, which we can identify with characteristic functions from omega into 2. Right here. So the cardinality of R is the cardinality of power set of omega. That's the cardinality of this, and this is 2 to the omega. So you're being asked to show that the set of countable subsets of the reals has got this cardinality 2 to the LF0. So notice, right, so solution here and so if X is countable, there's a 1-to-1 F going from X into omega. But then also there is going to be some G going from omega onto it. Yeah. So how do I get a G? I would say something like, let U0 be in X. Right, if if K is not in the range of F, let G of K be U0. So otherwise, when K is in the range of F, just let it be F to the -1. So where we had F here going into omega, here's omega. So F is going from X into omega. So the range of F may not be all of omega. We want a G going in that direction, which is onto. So we just pick some U0 to send the things that are not in the range of F onto. And we do that here in this clause. So the point of me saying all this is that if X is countable, there's an onto function from omega onto X here. And we're supposed to count the number of countable subsets of R. So being countable, right, I can also say that this is also an if and only if. Right? Having a 1-to-1 map into omega, we just see we've got a map from G from omega onto X. But that's also going to give us, if I've got a map G from omega onto X, that will also give me a map from F from X into omega, which is 1-to-1. So I suppose this is still part of my aside here. Conversely, if G goes from omega onto X, then there's F from X into omega, which is 1 to 1, which will show X is countable. So again, this is a standard move, how to get an F from a G, similar to what we just did. I take an F, sorry, I take an element of X, right? What will F be? Well, I will look and just take the least number that gets mapped by G onto U. And then this is 1 to 1. Sorry, so the upshot of this kind of rather lengthy preamble is that by definition, we say X is countable if there's a 1-1 map into omega. But, and I think it's an earlier exercise, this is equivalent to saying there's a map G from omega onto X. So we'll use that in the solution of the exercise. There's more than one way of doing this. I mean, I'm just picking something the way that first occurred to me. Okay. So at last, let X be contained in R, X countable. And then so it is the range of a map here. Thus any countable subset so X is, let's say X is a countable subset of R if and only if so I just express it like this as a map from omega into R such that X equals the range of F. So I've just written that out in mathematical notation here. So to count the subsets of R, which are countable, it suffices to count the functions which go from omega into R. Right? So the cardinality, the set of functions from omega into R, is going to be the cardinality of the countable subsets of R. So this is the answer. This is what we want here. So by rules of cardinal arithmetic, right, this is the cardinality of R to the power omega here. And R has got cardinality 2 to the Aleph 0, which is, we're expressing cardinals using Alephs in this question. So this is the cardinality of R, again to the power of Aleph 0. now rules of cardinal arithmetic here. And now aleph 0 times aleph 0 is just 2 to the aleph 0. Okay, so that finishes the first part of the exercise. So let's do 2 as well. Set of countable subsets of R which contain Q also has the same size. So Q, set of rationals, is countable. So this is also cardinality, 2 to the aleph 0. Right? So we don't shrink the number of countable subsets by insisting that Q is contained in them. Right? So the collection of all countable subsets of R has this size. So this more particular lot is not going to have any bigger size than 2 to the aleph 0. But on the other hand, it's no smaller than this. If X is any countable subset of R, X union Q, this is also a countable subset. So even if X didn't contain all of Q, this one does here. So this is a countable subset. Containing Q. So this is going to mean that the cardinality of these things here is going to be, well, at least 2 to the aleph 0, because I can take any one of these 2 to the aleph 0 x's, amalgamate it with Q, and get, again, a countable subset containing Q. So the cardinality of such sets, it's greater than or equal to 2 to the aleph 0 as well. And 3 here. The set of open intervals of R also has the same cardinality. To the aleph 0. Well, what are we talking about? An open interval is just something that looks like this. By this, I just mean the collection of x's in R, which are between R1 and R2. And these are typical real numbers. So the number of open intervals, cardinality of the set of open intervals, is just the cardinality of the set of pairs R1 and R2. Right? So you would just say something like this. It's just looking at functions from 2 into R, which just gives us pairs. Cardinality of R squared. And now it's just a little bit of, again, cardinal arithmetic. Cardinality of R times the cardinality of R. It's just the cardinality of R. Two cardinals multiplied by themselves, and this is 2 to the Aleph 0. So that finishes this. Any questions there about that one? Okay. Go on to 437. So here you're given a bunch of cardinals and you're asked to put them in increasing order or correct order using equals, less than, or equals. And let's see, what have we got? Aleph 13, Aleph omega squared, 0, Aleph to the omega 1, to the omega 1. Here, the supremum of the Aleph ends. Here, we've also quite a long list. Aleph omega 1 plus Aleph omega. Aleph omega 1 times Aleph omega 1. Aleph omega plus Aleph omega 1. We've also got on the list 2 to the 0, and then also Aleph to the omega 1. So you're also told in the question that the arithmetic here is all cardinal arithmetic, except for the omega squared that's down here. So remember, we are enumerating the cardinals by this Aleph function. Right? So this enumerates the cardinals. Right, so this function, this Aleph function here, is ascending ordinals into cardinals. Yeah. And Aleph omega squared, so f of omega squared is the omega squared cardinal, is this one here. And something like Aleph omega 1, this is the omega first cardinal. So it's a limit cardinal. It's a limit of all the Aleph alphas that are smaller than it. Okay, so what do we do here? Well, first of all, I just look at the list a bit and try and absorb what kind of things are obvious. Well, obviously 0 is at the beginning, right? It's the least cardinal, least finite cardinal, 0. 2 to the 0, that's 1. That's going to be the next thing, right? Right, so that's easy. Then what one does is look through the list for Alephs with the least index down here. Well, again, there's all of these are infinite indices. So we've got omegas and omega 1s, omega squareds. Here we've got finite indices. Right? So we've got Aleph n's. We're asked for the supremum of the Aleph n's. Well, that's Aleph omega by definition. Okay. But then here's Aleph 13, which has got a finite index. So this is going to come next. So if you asked for reasons, these are finite. Right? This is infinite here. And what's going to come next? Well, we choose amongst all these Aleph omegas here, which is the one with least index. Well, here is Aleph omega. Right? But here also is Aleph omega. So I'd say here, this is less than Aleph omega. So that ticks that one. We'll just cross them off as we do them. Here. Again, so the reason is 13 is less than omega. So that's why that is a strict less than. This equals the sup of the Aleph n's here. And again, this again by definition, this is the least cardinal bigger than all of these. And this is a cardinal. Right, so now it becomes a little bit trickier. So we want to see, we're going to have to use cardinal arithmetic to work out some of these things. So for example, but cardinal arithmetic is not hard. So it's always the larger of the two. Here, Aleph omega 1 is bigger than Aleph omega. So the answer here, this is going to be Aleph omega 1. Likewise, this is going to be Aleph omega 1 because they're both the same. This is just the other one written the other way around. Cardinal plus is commutative. So again, larger of the two, it's going to be this one. And here is Aleph omega sitting here all by itself. Sorry, Aleph omega 1. But this is the next candidate because this is a countable ordinal, whereas all these omega 1s, omega 1 is the least uncountable ordinal. So the next thing is going to be this. And that's bigger than Aleph omega. Right? So again, the reason for this is that omega is just less than omega squared. And then all of these other ones are going to come next. So here, Aleph omega 1 by itself, again, just to labor the point, it's because omega 1 is bigger than omega squared. And now it looks to me like most of the others, these plus and times ones are all Aleph omega 1. So that's going to deal with this and this and this. So these are all going to be equal to, and again, it's by definition of cardinal multiplication. Aleph omega 1 plus aleph omega. Actually, I say by definition, but actually it's Hessenberg's theorem, right? We're going to have this. This equals it the other way around. Right? This is by definition of plus. They're the same either way around. So that caters for this and this and this. And then the only one we're left with is this. Right? So I'm going to say that this is less than this. Aleph omega 1 to the power aleph omega 1. Right? This is because 2 to the aleph omega 1 is the same as aleph to omega 1 to the omega 1 here by a lemma, right? And by Cantor, this is always bigger than, by Cantor's theorem. 2 to the something is always bigger than the something, right? The size of a power set of a collection Y, right? The size of the power set is that of 2 to the size of Y. So this is Cantor's theorem here. And that's why that is going to be here, because although this is aleph omega 1, 2 to the aleph omega 1 is bigger than it. So I think as reason for this, I would say this equals this, and by Cantor it's bigger than that. Since by Cantor's theorem here, and that's why we've got this less than there. Okay, any questions about that lot? So if you look back, you'll find this kind of a typical part of an exam question that's come up over the years. So this is quite a common thing to do. So practice thinking about these kinds of orderings. And 438 is not dissimilar. Right? So simplify where possible. Two to the aleph 0. Aleph omega plus aleph omega 1. That's looking a bit similar to the previous exercise. 2 to the aleph omega to the aleph omega. Sorry, to the omega 1, it says. And then aleph omega cubed plus aleph 5 squared. And you're asked to do this twice, once without assuming the generalized continuum hypothesis, and then a second time assuming it. GCH, so this is the generalized continuum hypothesis. And that was for any alpha, 2 to the aleph alpha is the very next cardinal it can be. because we don't know how big the size of the power set of Aleph alpha is. But the hypothesis is that it's the next cardinal. So this is the GCH. And secondly, assuming it. Well, we don't know anything about cardinal exponentiation, really. Well, we have those few rules, but we don't know the actual values of these exponentials unless we assume the GCH. So the GCH would make 2 to the Aleph 0 the very next cardinal. It would make this Aleph 1. But we're doing it first without assuming the GCH. So without GCH, there's nothing more we can say about this. So without the continuum hypothesis, I can't simplify 2 to the Aleph 0. I can simplify this by Hessenberg. It's the larger of the two here, and that's Aleph omega 1. So whilst I'm at it, I'll do the other one hereby. Aleph omega cubed plus Aleph 5 squared. Well, Aleph omega cubed is just, well, let me write it out in glorious detail, although I don't think you have to in an answer. Aleph 5 squared is Aleph 5 times Aleph 5. Well, this is always the larger of the two. Well, these are all the same, and these two are the same. So actually, these finite exponents up here are neither here nor there. So this is just Aleph omega plus Aleph 5. And now, by Hessenberg, it's the larger of the two. So this one we can simplify to this. And the last one is this here. 2 to the Aleph 0 to the Aleph 1 is just by rules of cardinal exponentiation. 2 to the Aleph 0 times 2 to the Aleph 1 here. And so this is just rule of cardinal exponentiation. This is the larger of the two. So I'm using Hessenberg. And now, as it were, I'm stuck. I don't know anything more about this without assuming the GCH. So we've done what we can in our first run through with our simplifications. So with GCH, you could just say, we can additionally say 2 to the Aleph 0 is Aleph 1, and this one is Aleph 2. So that's all you need to say for the second run through, because the GCH doesn't affect the other answers. These are all simplified down to the most simple form they can be in here. Okay. Any questions then about that? So again, here is a variant on, again, something else from a past, certainly from a past exam paper at some point. Look at 444. Part 2. What's the cardinality of the Hilbert cube? So this is H, and it's a set of functions from n into 0, 1. So I could think of, a cube in 3 dimensions. I could think of being as a collection of functions from 3 into the unit interval. So it's a cube 1 by 1 by 1. Right? But this is a cube with, as it were, infinite dimensions. Right? It's a map from n into 0, 1 here. So what would we say here? I would say this is the unit interval 0, 1. So there's a bijection between this and all of R here. Perhaps by previous work or exercises. So again, check that that's the case. Right? So if I now look at the cardinality of H, it's this. But this is the cardinality of, well, a set of functions from n into this here. So writing the natural numbers here, as mathematicians normally do, of course, this is just omega here. So the cardinality of omega, this is just omega. This is bijective with the reals. So this is 2 to the LF0. And here is the cardinality of n. This is also LF0 here. And now we just use rules of cardinal exponentiation. It's just this here. And again, larger of the two, it's just 2 to the LF0 here. We're not told to assume anything about the GCH or continuum hypothesis, so I would leave my answer like this. Yeah. So 445 here. Let V be a vector space with a basis B. Now, to make it interesting, we'll assume that it's infinite dimensional. Right, so you're used to finite dimensional vector spaces, right, from your first year. Those with a finite basis. Well, we're going to assume we've got a vector space with an infinite basis. Perfectly reasonable concept. So we've got an infinite dimensional vector space here. So you then ask, how many finite dimensional subspaces of V are there? So what you're being asked then is a coded question about cardinalities. Right? Well, a finite dimensional subspace of V is generated by a finite number of elements of the basis. So any such finite dimensional subspace is generated by a finite subset of B. After all, B is a basis for the whole space. So any finite dimensional subspace of V has a finite number of generators, and they in turn can be all generated from a finite subset of B. So really what the question is about is how many finite subsets of B are there? So it's a coded question about the number of finite subsets of B. So we're being asked, what's the cardinality of the collection of finite maps into B Right, recall this is the union of all the maps from N into B. So this will give us n-sized subsets of B. This is all finite subsets of B right, here. But B is infinite. Here. So all this comes down to is just looking at the number of finite subsets of B, which is the size of B itself. Right. So it's worded as a question about mathematical vector spaces. In fact, it's a kind of rather simple thing about cardinalities. And there's nothing else to say. Yeah. Okay, are there any questions about that? Okay, if not, then fine. I'll see you this afternoon then. I'll say goodbye.